Hello everyone, and welcome to the Aqueous Solutions Lab video. Today we're going to try and tell you the stuff you need to know for the Aqueous Solutions Lab. Alright, so one of the important things you're going to need to be able to do in this lab is write molecular equations, total ionic equations, also sometimes called complete ionic equations, as well as net ionic equations. So let's start with the molecular equations. So molecular equations are going to show all the compounds as complete formulas. And so although these are electrolytes in solution here, and many of them are aqueous, we're not going to show their dissociation. And because we're sort of implying these behave like molecular compounds, that's why this is referred to as a molecular equation. Now this has some advantages and some disadvantages. One of the main advantages is that it looks really clean and nice on paper. It looks great. But one of the disadvantages is it doesn't at all accurately show what really happens in solution. Any of these materials, which are ionic or strong acids or strong bases, and are dissolved in water, in other words in the aqueous state, these are actually going to dissociate into ions. So while this looks pretty on paper, it does not very clearly represent what actually happens in solution. So you've probably written these types of things before, these types of molecular equations before. They're pretty common. But it is very important that you show your states. So make sure that you show your states when you're writing these things. If you leave your states out, then you will not receive credit for this. And this is very important because the reactions we'll be doing in this lab, a lot of the important part about them is that they change states. Like we might see gases form or solids form. So it's incredibly important you indicate those states. So moving on to the total ionic equation, which is also sometimes known as the complete ionic equation, what we're going to do is take anything that's a strong electrolyte. So strong electrolytes are going to include ionic compounds that are aqueous, as well as strong acids and strong bases, and we're going to show them as being dissociated. And so this is the same reaction as before, but now you can see we're showing anything aqueous that's a strong electrolyte as being dissociated. In other words, we're showing the individual ions. So for instance, rather than writing the K2Cr04 before, we're actually breaking that down into the individual ions right here. So again, it's very important that we show the states. Other things that are important to remember here, number one, make sure that you show the charges for any of the ions that are dissociated in solution. So any of the aqueous ions should have charges with them. Other important things are don't break down polyatomic ions into individual atoms. So you're going to have to remember which items are polyatomic ions, which ones aren't. So if we go back to the previous slide here, we can see K2. K2 is not a polyatomic ion, so we're going to break that apart into two potassium ions. But this CrO4, that's called the chromate ion, that one we are going to break apart. So chromate stays CrO4 2-. So be careful. Don't break apart polyatomic ions. Make sure you show states. So what are the advantages and disadvantages of this type of way of writing equations? Well, one advantage is it's much more accurate. This really clearly reflects what's actually happening in the solution. So anything aqueous is actually broken apart and all those ions are floating around in solution. What's the disadvantage? Well, it takes up a lot of space and it's pretty tedious to write, and a lot of people don't think it looks quite as clean on paper. So you'll see these total ionic equations less common in textbooks and things like that, but you do need to be able to write them out like this. You do need to know how to turn a molecular equation into a total ionic equation. That's one of the skills you'll be required to have. So one thing I want to bring your attention to here is we have a couple ions that are what's known as spectator ions. And spectator ions do not participate in the reaction. So if you look right here, we have these potassium ions before, we have these potassium ions afterwards, and they've undergone no change. They weren't affected by the reaction. They've just kind of hung out and watched. And similarly, our nitrate ions, I'm going to circle those, and our nitrate ions over here, these also have not actually participated in the reaction. So again, just like you'd say like spectators hang out watching a sport, our spectator ions haven't actually participated in the reaction. And these spectator ions are going to be important in the next type of equation, and that is the net ionic equation. So the net ionic equation is going to be similar to the total ionic equation, except we're only going to show those ions that actually undergo a change. So again, we're only going to show those ions that actually undergo change. And so what does that mean? Well, spectator ions are going to be left out, so make sure you leave out any spectator ions. So again, same reaction as before, but notice that we've left out the potassiums and the nitrate ions, so they don't actually participate in the reaction. And for all of these, remember, always show those states. Very important to show the states here. All right, so moving on. Another thing you're going to need to be able to do is use the solubility rules. And so we have a set of rules right here that corresponds to which compounds are generally soluble. So anything containing lithium, sodium, potassium, or ammonium ions, anything with one of those four, any ionic compound with one of those four cations is going to be soluble. And there's no exceptions to this. So anything you see that has one of those four cations will always be soluble. Similarly, anything that contains the nitrate or acetate ion, these will also be soluble, and there's no exception. So anything containing one of these two anions will always be soluble. Other things that are usually soluble are going to be chlorides, bromides, and iodides. So any ionic compound that contains chlorine, bromine, or iodine is going to be soluble. And we have just three exceptions here. If we contain silver, mercury, or lead in conjunction with those ions, that'll be insoluble, but any other metal combined with these ions will give us something soluble. And we also have the sulfate ions. Sulfate ions are generally soluble in ionic compounds, and the only exceptions are shown here. Again, if we combine it with one of these five cations right here, that means that the sulfate will actually be insoluble. So what about if we have something that's not on this list? Like what if we have magnesium bromide? Well, we could say bromides are going to be soluble, and magnesium's not on our list of exceptions, and therefore magnesium bromide would be soluble by these rules. What about if we had, let's say copper sulfate? Well, if we have copper sulfate, sulfates are usually soluble, and the only exceptions are listed here, and we notice that copper is not on the list, so copper sulfate would indeed be soluble. But what about calcium sulfate? Well, calcium sulfate would actually be insoluble because although sulfates are usually soluble, calcium is actually one of our exceptions here. So calcium and sulfate forms an insoluble combination. All right, now let's take a look at things that are generally insoluble. So ions that are generally insoluble are going to include the hydroxide ion. So the hydroxide ion is insoluble generally, except when combined with those four ions we mentioned on the previous page that are always soluble. So everything is soluble with these, so hydroxide is soluble with these, and it's slightly soluble with calcium, strontium, and barium. So what does that mean? That means we can dissolve a little bit of calcium hydroxide, a little bit of strontium hydroxide, or a little bit of barium hydroxide into water. They aren't particularly soluble, so it's sort of ambiguous if we'd form a precipitate, if we have a reaction that forms one of these three metals combined with hydroxide. So for the purposes of our lab, assume that things that are slightly soluble are not going to form a precipitate. So what can we infer from this? Well, anything that's not on this list of exceptions here, so anything that's not on our list of exceptions here, is going to actually be insoluble with the hydroxide ion. So if we combine the hydroxide ion with any other metal, like let's say iron for instance, iron hydroxide would be insoluble because these items on this page are generally insoluble. And how do we know that? Well, iron is not one of the exception metals right here. Or similarly, if we had lead hydroxide, that would also be insoluble because lead's not on our list of exceptions. But if we had potassium hydroxide, for example, that one would be soluble because all potassium compounds are soluble, and potassium is also listed as one of our exceptions here. So these rules are kind of tricky to use. They take some getting used to. Theoretically, you've learned them in previous chemistry classes, but you may not remember them or may not have understood them, or they may be new. So these are something you might need to practice. And then right here we have the sulfide ion. Similar to the hydroxide, the sulfides are generally insoluble. So almost any metal we combine with sulfide is going to be insoluble, except we have a similar list of exceptions. But notice that the calcium, barium, and strontium now are not slightly soluble, they're significantly soluble. So these are exceptions, but any other sulfide would be insoluble. And then finally we have carbonate and phosphate. Carbonate and phosphate are almost always insoluble. The only time they're soluble is if we combine them with one of those 4 metals we listed on the previous slide. So if we pick any other metal, like aluminum for instance, aluminum carbonate or aluminum phosphate would be insoluble because these are almost always insoluble. If we pick, let's say for example, zirconium phosphate or zirconium carbonate, those would also be insoluble. Carbonates and phosphates are only soluble with these 4 metals right here, these 4 cations right here. So I'm going to end the part 1 of the video there, and we'll pick up with part 2 momentarily.